Hello everyone, so welcome back to our next lecture session. So I believe we were talking about kinetics, right? And we were talking about rates of the reactions and how they depend upon the concentration of the relevant reactants. And then we discussed how temperature affects the rate constant, I guess, right? We looked at the Arrhenius equation, and then we started discussing the mass balance equation, and we also talked about the different or the three kinds of reactor: the batch reactor, the plug flow reactor, and the continuously stirred tank reactor. So we'll have a very brief review about the mass balance and its applications to the batch, plug flow, and CSTR, and then we are going to move on to some of the applications, I guess, right? So let's have a look at what we have been discussing. So we have been discussing about mass balance, right? And a fundamental equation, what is that, I guess? dC by dt plus the del product of the flux is a vector here, right, is equal to the sources and sinks. And again the flux, we have two fluxes here, one due to advection and one due to diffusion. Advection, when you have net fluid flow in one direction, let's say, or in any direction, right, we talked about that. And this is due to the flux due to diffusion, and in general driven by concentration gradient. And this is what we have discussed. So, and the flux due to advection, we said, is going to be equal to what now? Pardon me, right? And this is what we have here. And due to diffusion, it's going to be diffusion coefficient times the del product into C. So substituting the relevant, and here it's going to be negative. Why is that? Let's say the diffusion is such that it always drives or tries to minimize the gradient in concentration. So if the concentration is higher here and lower here, the compound would move from point A to point B. Again, random motion again if it's B here. So it's going to move in these directions, right? Random motion, so that after a certain time you are going to have concentration at the same what do we say, levels throughout, let's say. I think I'll try to have a better representation here. So let's say initially all my concentration is right here, right at let's say x, this is x, distance x, and this is my concentration peak here, let's say initially, right? So with diffusion what starts happening, I guess, this peak, right, at this point x, it's going to start flattening out, right? So finally you are going to have something like this and so on. So this more or less is due to diffusion. It's going to be the same in all the directions. It's relative, it's random, and it's also relevant. I mean the relevant diffusion equation is going to be negative, obviously, because it's going to decrease, and then the diffusion coefficient and del product of the concentration here. So once we plug these values back in our main mass balance equation, what do we end up having, please? So dC by dt plus the del product of C, let's say C is also a gradient here, let's say, is equal to d del square C plus sources and sinks, right? And if I assume that the velocity is constant, let's say, dC by dt plus u del dot C is equal to d del square C plus sources or sinks, right? And this is what we discussed. And in the same manner we end up simplifying this equation when there is no diffusion, or assuming there is no diffusion, let's say, and then simplifying it further at a macroscopic level, at a macro level. What do we have? I guess we have V dC by dt is equal to Q in C in, this is coming in, this is Q out C out, right, going out, plus volume into rate of formation minus rate of loss. This is the one that looks at the relevant reactions, right? And this is what we have, and this is the accumulation term. right. This can obviously be negative depending upon these factors here, right. And we discussed this particular aspect, and we then applied them to 3 different kinds of reactors. I believe they were batch, and what else please, plug flow reactor, and what else please, CSTR, right. And batch reactor, no flow coming in or going out, right. Plug flow reactor, flow through a plug or flow through a pipe, let us say, right. And compounds coming in at the same time will obviously going, but our definition exit at the same time, right. Yes, and so on. And CSTR, obviously I guess we have flow coming in, we have flow going out, and we have continuous mixing here and the concentration of the relevant compound here. And I believe we looked at the relevant derivations, so we are not going to go into that in detail. So, and then I believe we started talking about a particular example. I believe it was A goes to B, right. That was with respect to the batch reactor, and I think we looked at Ct equals C naught goes to e power minus kT and so on. So, next we are going to come up with another type of example, and this example now we are going to look at is obviously again first order. We are going to start with the baby steps. First order, irreversible, right. But to mix up, or let us say to make it slightly more difficult, rather than looking at A goes to B, we are going to look at A goes to 2B, right. And obviously here let us write down rate of loss of A, and that is going to be equal to rate constant of this particular equation, which is let us say K times concentration of A, right. And we are all aware that the rate of any particular reaction and thus the rate of loss of those particular compounds always depends upon the reactant and not the products. So, right, that is why we have rate of loss of A equal to KCA. Or if you want to relate that to the rate of the reaction, how do we do that? Rate of the reaction is equal to rate of loss of A by the stoichiometry coefficient, which is 1, and negative if you want to here, and then that is equal to plus, because it is being formed, rate of formation of B by the stoichiometric coefficient, which is 2. So, here one particular aspect that needs to be looked at is the symbol. So, here I guess you need to put in your understanding. So, if I am calling it already loss of A, I guess it is better not to have a negative term here. If I am not talking about loss here, then I can have the negative term. If I am already talking about the loss here, so it is always better to look at the magnitude. We will see why. I guess that is obvious, because when we have in our mass balance equation, we already have rate of formation minus rate of loss. So, if you again write rate of loss equal to the negative of something, right, this is going to end up being positive here, the second term here. So, that is what we do not want to have. So, you will just write rate of formation minus rate of loss, and we will just write the magnitude of that rate of loss, which is what we have in this case to be KCA, right. So, that is what we have here. The rate of loss of your particular compound A is KCA, right, and that is something we just looked at. Yes, and obviously this is the source equation where we looked at. Yes, because I identified it as loss, I am having a positive here. If I did not, I will have the negative symbol there, right. So, let us see what we are up to next, I guess. So, we are obviously going to apply this on the batch reactor there, and it is for mass balance on compound A, and then you know the system boundaries, right. So, mass balance is, as we know, dCA by dt is equal to rate of formation of A minus the rate of loss of A. This is what we derived for our basic batch reactor a couple of sessions ago, the last session I believe, last theory session anyway, right. So, what do? We are going to plug in the L2 equations here, and as we can see, we have a rate of loss of A here, but is A being formed in any manner? No. So, the rate of formation of A is going to be 0. So, again dCA by dt is going to be equal to 0 minus, and here we have K into concentration of A. So, that is equal to minus K into concentration of A. So you solve that, right, first order homogeneous differential equation. So you end up with Ca is equal to Ca naught into e power minus kT, right. I believe obviously this is similar to what we solved for when we looked at A goes to B2, right. That does not come up in the picture here, not yet anyway, and we will see why. So anyway, here we have the concentration of A, right, but obviously let us say someone is going to ask you how do I calculate the concentration of B2, right. So there are different ways again, but an easier way would be to look at the stoichiometry. So we are going to look at applying stoichiometry, right. And I guess in this case we talked about this earlier, right. Rate of a particular compound of A, stoichiometric of A is equal to rate of loss or formation of B by stoichiometric coefficient of B, and in this case while A is being lost, B is being formed. So this is what we have with respect to the stoichiometry here, right. So we are going to substitute with the material balance. So more or less what does this mean? Minus dCA by dt, that is rate I guess, right, by stoichiometric coefficient of A will be equal to plus dCB by dt by the stoichiometric coefficient of B. So in this case what do we have? The equation we have is A goes to 2B, right, we have A goes to 2B. So let us plug them in here. So that is going to be and again it is C differential, right. So what is that going to be? C2 minus C1 as in Ca minus Ca naught by stoichiometric coefficient of A, right. We are talking about with respect to time obviously, and so again the change here and that is going to be equal to what is this please here, Cb minus Cb naught here, right, by stoichiometric coefficient of B. So this is obviously after integration, right, the change in so this comes about after integrating the previous equation, right, and this is what you see here, right, Cb by minus Cb naught, yes. So let us plug in the relevant values, and here we are going to have so this is a particular what do we say equation you are going to use throughout the class. So I think it is worth remembering where we have that from. So more or less minus Ra by Va equal to Rb by Vb nu B, and that more or less is rate is dCA by dt, Rb is dCb by dt. So and then integrating this particular equation here, integrating this equation here, and then plugging in the relevant values, we end up with these particular sets of values, right, with this set of equation, yes. So now let us plug in what we have here so far. I guess we know that Ca is equal to what now? I think we have Ca is equal to Ca naught into e power minus kT, right, that is what I believe we have from our previous equation, yes. And we also know that the stoichiometric coefficient of A is 1 and the stoichiometric coefficient of B is equal to 2. So if I plug those values in here, what is it that I am going to end up with here? I guess I am going to have Ca naught minus Ca, we will substitute for that I guess, is equal to Cb minus Cb naught by 2, right. Let us see if we made any issues with the symbols. No, I think we are on the right track there, right. So let us solve for B and then plug in for Ca later on. So Cb or thus would be 2 times of Ca naught minus 2 times of Ca would be equal to Cb minus Cb naught, right, and that would mean Cb is equal to 2 times of Ca naught minus 2 times of Ca plus Cb naught, right. So that would then mean 2 times of Ca naught plus Cb naught, right, minus 2 times of, and what do we have here? We know that Ca is equal to Ca naught into e power minus kT. So plugging that in here, Ca naught into e power minus kT, right, this is what we have. So I am going to continue working it out here, and let us simplify that further I guess. So we have Cb is equal to Cb naught plus 2 times of Ca naught into what else do we have here? 1 minus e power minus kt, right. So, now that and what was the Ca equation, I guess Ca equal to Ca naught into e power minus kt. So, I believe we are on the right track there, and we are done with that. So, what are Ca naught and Cb naught? Obviously, they are the initial concentrations of A and B respectively, right. And with this you can now solve for A and B at any given time t, right. That is what you see here, yes. And thus obviously we are not going to go through that in detail. So, if you want to, you can plug in time equal to 0 and time equal to infinity and check your particular equation. So, let us plug in time equal to 0. So, let us see what will Cb transform to. It will be Cb naught plus 2 times Ca naught into 1 minus e to the power of 0 is 1 minus 1. So, that is equal to Cb naught. So, that is a check, right, at time equal to 0, Cb equal Cb naught, that is something that we know, that is a solution for our answer, not solution, I guess, that is a check. And similarly here again, if I plug it in Ca equal to Ca naught into e power minus kt, right, and if I plug in time is equal to 0, right, what will that be? We will see again Ca equal to Ca naught, and that again is a check here, right. So, again if we plug in infinity, what would infinity be? It is going to be at equilibrium, let us say. Let us see if we can plug that in here. I will try to erase this here for a particular second, I guess, right. So, if we plug in infinity, what is it that you think we are going to look at, right. So, if A is going to B, right, or to B, you would expect that all of A is going to be consumed, and hopefully that is what we are going to see here. So, at time t is equal to infinity, right, and that is what you see here, and you plug in t equal to infinity, you see Ca equal to 0, yes. So, that is what you expect, and Cb will be equal to Cb naught plus 2 times Ca naught into 1 minus 0, that is equal to Cb naught plus 2 times Ca naught. So, this again is at time is equal to infinity, right. So, what does this mean? So, at equilibrium, I guess you will have, what is it, pardon me here, all the initial Cb naught present and also twice the concentration of A present. Why is that? Because we know that for each mole of A we are forming 2 moles of B, right. So, that is what we see here. So, now the check with respect to time equal to 0 and time equal to infinity is done. This is with respect to the batch reactor. So, next we will move on with respect to the derivation for the plug flow reactor, right. And what is the basic equation here? Again we are still talking about A goes to 2B, and we are trying to solve for concentration of A and concentration of B. What are they, I guess, right. So, plug flow, what is the basic equation here? And I believe it is dC by d theta is equal to rate of formation minus rate of loss. And again theta, what does that mean? Theta is the hydraulic retention time, right. And what was this equation from, or where did we get this from? U dC by dx is equal to rate of formation minus rate of loss. So, what does this mean? Again concentration is changing with distance and not with time. That is something you need to keep in mind. So, obviously x by u, right, we are saying that is hydraulic retention time, right, or more or less V by q is theta, and that is where we end up with x by u is equal to theta there, right, and that is how we have here. So, we are digressing. So, we have dC by d theta equal rate of formation minus rate of loss of compound, and you have this particular setup and so on. So, I guess we can work everything out, but as you see the only difference between the batch reactors equation dC by dt equal to rate of formation minus rate of loss, this is for the batch reactor, right, and the one for the plug flow is that you just replace T with theta, right, and this obviously is at steady state. That is one thing you obviously need to keep in mind. So, at steady state the solution for your plug flow reactor for the above scenario, what is it going to be? It is going to be the same as the previous case, but you just need to replace T with theta, right. So, and with that we will be done with the plug flow reactor, and let us move on to the continuously stirred tank reactor, I guess, right. CSTR now. And the first aspect is going to be again mass balance. So what's the basic mass balance? I believe it was CA minus CA naught whole by theta is equal to rate of formation minus rate of loss. Again, no differential equation here, and again this is the equation for the CSTR at, what is this please, at steady state obviously, right. This is at steady state. So let's go on with looking at what we have here. So again we have A goes to 2B, right. So if I am applying it on this particular case, so CA, or let's switch them around, or no need to, I guess, CA by CA minus CA naught by theta is equal to, is A being formed in any manner? No. So that's going to be 0 minus K rate of loss of A is again what now? K into concentration of A, that is what we have here, and minus KCA, right, and that's what we have here. And so again we can end up solving for CA is equal to what do we say, CA naught, right, plus, now it's plus I guess, minus theta into KCA, is that right? Let's look at if our calculations for 1 second here please. Okay, so I believe I can understand what the issue here is. So here we have KCA term here, right. I need to bring that over to the left obviously, right. So anyway, CA is equal to CA naught minus theta into KCA. So if I bring this term over here, CA into 1 plus theta into K is equal to CA naught, right. And then what next please? And then it's going to be CA is equal to CA naught by 1 plus K theta, right. So this is with respect to your CSTR. So the key here is, I believe you might have missed it. The issue here is that, you know, the term here is you have input coming in Qn or Cn, right, and here is Ca naught. So here we are defining in and out Ca naught and Ca, right. This is what we have. So for a CSTR, right, then this is the key here, and that's how we end up with the rate. So you want to know the rate of this particular loss of compound of A here, right, and this we say is equal to C. The concentration of the compound of A inside the reactor is C, and that we know is Kc, rate of loss of the compound. But why are we saying it's equal to Kca now? So the key is that because this is continuously stirred, whatever the concentration is inside the reactor will be the same as the concentration leaving the reactor, right. So that, what does that mean now? So if you have Cn and you have C out, right, and this is C, what does this mean? C and C out are going to be the same, right. Makes sense hopefully, because this is a continuously stirred reactor. So whatever is coming in, it's going to be instantaneously diluted, and then you will have the relevant equations, and then it's going to flow out, right. So obviously in a CSTR, the key is that the concentration inside the reactor and the concentration outside the reactor are the same. So that is the reason why when we are writing the rate of loss of this particular compound, we could directly write that as concentration of A that's leaving the system or even within the system, which is going to be the same, right. So that's the aspect here. So where are we here? So Ca equal to Ca naught by 1 plus K theta. So let's have this, and again let me write that down. Ca is equal to Ca naught in by 1 plus K times theta. So this is what we have. So now again we need to find out what concentration of B is, right. So same case as earlier, we are going to apply the stoichiometry. Apply stoichiometry. Again the stoichiometric equation for this is A goes to 2B, right, and for this let us see what we are going to have. And so again we know that rate of A by stoichiometric coefficient of A is going to be minus here and plus here because it is being lost. B by stoichiometric coefficient of B. This is what we looked at earlier, and so from this you know that we have the relevant equation after integrating and so on. What is it that we have? We have Ca naught minus Ca, right? But here instead of time it's going to be obviously theta, right? Theta into what is going to be here, Cb naught minus Cb by theta, and obviously here you are going to have the same stoichiometric coefficients here, 1 by mu A minus 1 by mu A, and here I am going to have 1 by mu B, right? So it is not time anymore, it is the hydraulic retention time here, right? So that is the key here. So once you have this, and let us plug in the relevant values for the stoichiometric coefficients, I guess, right? So it is going to be Ca minus Ca naught by the stoichiometric coefficient of A is just 1 here. So 1 or theta here, that is going to be equal to Cb naught minus Cb by 2 theta. So theta theta obviously they cancel out, right, 1 time. So this is what we have. So again what do we have here, please? We have Cb is equal to 2 times concentration of A minus 2 times concentration of A naught, or the initial value, minus, or are we going to have minus term here? 1 second please, I guess let me simplify that for myself. 2 times of Ca minus Ca naught, right, is going to be equal to Cb naught minus Cb. So if I take this whole term here to the left hand side, Cb is equal to Cb naught minus 2 times Ca minus Ca naught, right? And let us see what we have here. So Cb naught minus 2 times, and Ca we know is, and from here this equation here, right, what is Ca here, please? Ca naught by 1 plus k theta minus again Ca naught, right? So that is going to be equal to Cb naught minus 2 times of Ca naught, I am going to take that out, I guess, 1 minus of 1 minus k theta by 1 plus k theta, and that is going to be equal to, I am going to finish that up out here, and what am I going to have here? I guess I am going to have Cb is equal to Cb naught minus 2 times the concentration of A naught, right, into 1 minus 1, so minus k theta by 1 plus k theta, right, and if I take this or make this positive, this is going to be a positive term here, and this is what we are going to end up with, right. So let us try to wrap up this session here for today. So what have we been looking at in today's class? We have been trying to apply, what do we say, the case with respect to a reversible half reaction, or irreversible, pardon me. So we have been looking at A goes to 2B, right, and we looked at applying them for the batch, for the plug flow, and for the CSTR, right. So batch reactor, I guess, first we do connect the mass balance on A, we end up with Ca or is equal to Ca naught into e power minus kT, pardon me, and the same case is that and I believe we end up calculating Cb to be some value now which I am unable to recollect. Let us see if I have that here on my set of slides here. Cb is equal to, where do we have this here, and here is Cb 2 Ca naught plus Cb naught. Anyway, we have the relevant equation there, right. And for the plug flow though, what do you do here? We only change T, or replace T with theta, and we end up getting again Cb values and Ca values here, right, same case here. And CSTR2, I guess, you know, it is a different case, we work them out, Ca and Cb. Let us see what it is that I have here. Ca is equal to Ca naught by 1 plus k theta, and again we end up with the relevant equation here. So how did we end up with Cb though? Ca from the mass balance, right? Cb, how did we get that? That's from your stoichiometry. Again, rate of A, stoichiometric coefficient of A equal to Rb by stoichiometric coefficient of B, and because A is being lost, we are having that as a negative. And then I guess for batch, we said it's dC by dt, for plug flow dC by d theta, and again so on so forth with the CSTR, and we were able to relate the concentration of B, we were able to express it as a concentration of function of a concentration of A, right? And that's what we were able to do here with this particular equation. And then we calculate the concentration of B for all the 3 cases, right? So with that, I guess I'll wrap up for this session, and we'll continue the relevant aspects or one other reversible reaction case in the next session, please. Thank you.